Welcome to this explainer from Forge College. I am absolutely thrilled you're tuning in today. We're going to unfold the engineer's blueprint for keeping your Bitcoin transactions incredibly private and highly efficient. If you've been following along with our Bitcoin fundamentals track, you know we've been building up to this topic since our Schnorr Signatures deep dive. Today it's all about MAST and script flexibility.
Think about this for a second. Why reveal your entire blueprint just to open the front door? It sounds slightly ridiculous when you frame it like that, right? But imagine having to publish a 50-page legal document detailing every single one of your financial contingency plans to a public blockchain every single time you buy a cup of coffee. That is exactly the clunky, highly public flaw we used to deal with in old Bitcoin scripts. We desperately needed a better way.
So here's the game plan for today's explainer. We'll start with the old script problem, introduce the MAST solution, head into the workshop to build our branches, find the Merkle root, and lock it all in with the Taproot commitment. Finally, we'll wrap up with a quick QA check on privacy and efficiency. Let's dive in.
Section 1. The old script problem. Basically, why publishing the entire blueprint was a massive headache. In the dark ages of the old way, you had to publish every possible spending condition on-chain. Multi-sig setups, backup time locks, emergency keys, the whole shebang. The entire world got to see all of it the moment you spent the funds, even the backups you never actually used. It was expensive, it was clunky, and it offered literally zero privacy. But MAST gives us a vastly superior motto: commit once, reveal minimally. We can now lock an incredibly complex script into a single, tiny, highly efficient commitment.
Moving to Section 2, the MAST solution. Let's look at this elegant engineering fix.
MAST stands for Merkelized Abstract Syntax Tree. Don't let the name intimidate you. Simply put, it's a data structure that replaces explicit full script reveals with a single, fixed-size commitment called a Merkle root. Think of it as an invisible prototype, kind of like a tree with multiple branches of spending conditions. When it's time to spend, the branches you don't use simply get snipped off and stay hidden from the public forever. Remember our previous deep dive on Schnorr signatures? Well, that mathematical linearity we learned about is exactly what allows us to hide these alternative script branches behind a single output key without leaking them until they're actually needed.
Section 3, building the branches. This is our workshop phase.
Let's say we're working with two distinct branches here. Leaf A is a simple single public key check, a standard signature. Leaf B is a CSV time delay plus a public key. And no, CSV here isn't a spreadsheet file, it stands for Check Sequence Verify. Notice that both of these leaves are prepped with a critical 0x00 version marker byte before their serialization. This 0x00 prefix is a tiny but absolutely vital engineering tolerance. It specifically marks these inputs as leaves in our Taproot Merkle tree.
Section 4. Finding the Merkle root. Time to assemble the parts. Here is our basic assembly manual. Step 1. You serialize those leaves. Step 2, you hash them, making absolutely sure to prepend that 0x00 prefix we just talked about. Step 3, you sort the hashes lexically. This deterministic sorting is a protocol-critical choice because it ensures anyone verifying this proof will get the exact same result. And finally, Step 4, build the Merkle root. But notice a slight change here. We use a totally new prefix, 0x01. The crucial point really comes down to this formula. The node hash equals SHA-256 of 0x01 concatenated with the left hash and the right hash. That single deterministic formula locks our two independent branches together into one neat fixed-size Merkle root. That 0x01 byte specifically tells the protocol, hey, this is a node combining two things, not just a leaf.
Section 5, the Taproot commitment. This is the final lock.
Notice the tweak formula here. The tweak equals SHA-256 of the internal key combined with the Merkle root. Because of the additive magic of Schnorr signatures, we can seamlessly blend our internal public key with our newly built Merkle root to create a single Taproot output commitment. To the blockchain, this just looks like a normal, boring public key. No one knows the complex tree hidden underneath. By the way, if you want to master the math behind this and really get into elliptic curve operations, our learning programs at Forge College go way deeper into the cryptography of how these tweaks actually modify the keys.
Section 6. Privacy and Efficiency. Time for the final QA check.
When you actually go to spend your Bitcoin, let's say you're using the time lock condition we built into Leaf B, you only reveal that specific leaf, along with the tiny Merkle proof representing the sibling hash of Leaf A. That is literally it. The actual script contents of Leaf A stay completely invisible to the blockchain, You don't leak your backup plans to the public, and you don't pay network fees for data you didn't even use. It's a massive win-win.
So let's bring this all together. First, byte-level details like serialization matter immensely. Those 0x00 and 0x01 prefixes have massive consequences for the final hashes. Second, deterministic sorting is protocol critical for the network to actually agree. Third, unused branches remain completely private. And fourth, by committing once and revealing minimally, we achieve incredible gains in both privacy and block space efficiency. It's just a remarkably elegant solution.
I want to leave you with this provocative thought. Are you ready to test the true efficiency of Taproot for yourself? To explore how these designs stack up in real-world transaction size trade-offs against those older, script-exposing designs? And to check out way more Web3 topics? Head over to forge.college. Thanks for joining me for this explainer, and we'll see you in the next one.